Okay, ratio test for absolute. Now, there was a question here somewhere?
Yeah, why can't you use the rules that we got before?
They're not going to be sufficient. You'll see. I'll give you one right now.
Okay.
Let's take a look at this series. Two to the n over n factorial. Okay? Now, problem here is the factorials. You can't use an integral test on it for sure because factorials are discrete functions. They're defined only at the integers and not in between. So we don't have an integral test. Okay? We don't have a difference in degrees because there's no degree for an exponential function and there's no degree for a factorial. So we can't use our difference in degrees little shortcut there. Okay? The comparison tests depend on finding a comparable series that we know converges or diverges. We don't have one here. Okay? This is one, and this is one we don't have a test for. We're going to use a ratio test, okay, on this one. And let me give you the ratio test, and then I'm going to give you a shortcut that takes care of most of those ratio test problems, okay? I'll give you a shortcut for that. But we're going to do it out on this. The ratio test says this. Given series of the form A sub n, where A sub i's are not zero. We can't have any zero terms. All right? As long as we have non-zero terms. They have to be non-zero terms. I'm sorry the A sub n is up so high there, okay? I was thinking of something else. Then, let the limit as n goes to infinity of the absolute value of A sub n plus 1, the n plus first term, over the absolute value of the nth term be equal to L. So you're going to take the n plus first term divided by the nth term. You're going to take the limit as n goes to infinity. Call that limit L. Then, if L is greater than 1, the series diverges. If L is less than 1, okay, if it's less than 1, the series converges, and I'm going to put parenthetically, absolutely. If this is an alternating series, which is legitimate as long as the terms aren't zero, that will have absolute convergence because we're doing the absolute values. We're testing their positive series. If they're not an alternating series like this one here, it's just simply going to converge. Okay? If L equals 1,
Converges partially? Or?
No, the test fails. All right, the test just simply, you can't use it. Okay, the test fails. You have to do something else. All right, so here we go. Let's take a look at this series. Let's use the ratio test. We're going to take the limit. B goes to as n goes to infinity. Absolute value. I can use one absolute value symbol here of the n plus first term, 2 to the n plus 1 over n plus 1 factorial divided by the nth term, 2 to the n over n factorial. That's what I'm doing. I'm taking the n plus first term, and I get that by replacing n with n plus 1. And then I'm dividing it by the nth term. That's this one here. And I'm going to find this limit as n goes to infinity. That's equal to the limit as n goes to infinity of the absolute value. Now, the absolute value symbols aren't necessary here. I've got positive terms anyways. So what happens? You get 2 to the n plus 1 in the numerator. This denominator here comes up to be in the numerator. You can multiply by the reciprocal. Okay, think of this as this fraction divided by this fraction. Okay, and what you can do, instead of doing this division, you multiply by the reciprocal, flip this around. So the n factorial comes up in the numerator, And the 2 to the n comes back down here with this n plus 1 factorial. This is the limit we have to do. Hey, Eric, how you doing? Good deal. We're doing the ratio test for absolute convergence here. All right, now we're going to have to simplify. Let's simplify. Okay. Well, what happens to 2 to the n plus 1 over 2 to the n? How does that simplify? 2. Yes. And again, I don't need the absolute value since I had all positive terms. All right, I'm just going to use the parentheses then.
So what happened?
What happened is he subtracted the exponents here and got 2. N plus 1 minus n. The n's cancel. You get 2. Now, what about n factorial over n plus 1 factorial? What does that simplify to?
It doesn't simplify?
It simplifies.
Oh, you get rid of the, maybe 1 factorial, which is 1. On the bottom, 1 over.
No, it's not. N plus 1.
It
N,
stays the same.
what's that?
The n plus 1 factorial.
Don't you distribute the factorial?
Here? No, you can't just distribute
It's
this.
going to be just n plus 1.
It's going to be n plus 1. That's exactly right. Here's what happens.
But what happens to the 2 to the n?
2 to the n plus 1 over 2 to the n becomes 2 because you subtract the exponents. N plus 1 minus n is 1. That's 2 to the first. N factorial over n plus 1 factorial. Here's what happens. N factorial, n plus 1 factorial. What is n plus 1 factorial equal to? It's n plus 1 times n factorial. And these will cancel. You get n plus 1. 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. 7 factorial is 7 times 6 factorial. That's exactly what you have here. N plus 1 factorial is n plus 1 times n minus 1 times n minus 2, 3 times 2 times 1. N plus 1 factorial is n plus 1 times n factorial. The n factorials cancel. You're left with an n plus 1. Okay? What's the limit as n goes to infinity here? 0 is correct. Thank you. And as long as that limit's less than 1, the series converges. Okay? That series converges. All right? It's a converging series. All righty? Let's do another one. You can do some complicated series with the ratio test. Very powerful test. Okay? We're going to do another one. And you use it when you got combinations of exponentials with factorials. Let's do another one. Here we go. Let's take a look at this series. Let's do an alternating series. Let's suppose we have something like n squared over e to the n. Okay.
But, sorry,
Go ahead.
just for the one before.
Yep. Okay, no problem.
I thought you can get 0.
You can get 0. As long as L is less than 1, there's no restriction. 0 is okay, as long as it's less than 1.
Then what did you say? AI equals.
The AIs cannot be 0. You can't have 0 terms. And we have no 0 terms here.
What do you mean 0 terms? That's in like.
Some one of the terms being a 0. What happens is if you got a term that's equal to 0, you got a problem of a division by 0 when you do the ratio test, one term divided by another.
Oh,
So you just got to eliminate the 0 terms.
Equal 0.
Yeah, none of those terms can be 0. And they're not. Okay, and they're not.
Sorry.
Yeah, that's okay. It's okay. All right, let's take a look at this. Now, let's just think about this a minute. We have an alternating series here, but the negative 1 to the n causes that to be alternating. We have an n squared, which is going to go to infinity, and we're going to have an e to the n, which is going to go to infinity, okay? The question is, who gets to infinity first? Which one is increasing fastest? N squared or the e to the n? Which one increases fastest? That's the key issue here, okay? What do you think? E to the n does. Exponential functions increase faster than polynomials. If this is an n to the 10th power, plus n to the 9th, plus 17n squared, plus 100,000 n, plus 27 billion, it doesn't matter. Exponential functions increase faster than polynomials do. And you can show that with a L'Hopital's rule. L'Hopital says take the derivative of this one over the derivative of that one. Well, when you take the derivative of polynomials, the exponent decreases by 1 every time. And eventually gets down to a constant. But what happens to an exponential function like e to the x? It's indestructible. You can take an infinite number of derivatives, and it's going to stay an exponential function. So it's indestructible. It stays the same. So what's going to happen there is this. Now watch what happens with the ratio test. We'll take the ratio test here, but because this one's increasing faster than this, what you should be thinking is that term is going to go to 0 quite quickly. Therefore, that series will converge, and converge absolutely, okay? Because its positive series will converge. Let's do it. And then I'm going to give you a trick that is just awesome trick. Okay, I'll give you an awesome trick here. All right, let's do the ratio test. Take the limit, okay, as n goes to infinity. We're going to take the absolute value of the n plus first term. Oh, okay, hold on, easy guy. N plus first term over the nth term. Okay? Is everybody okay with that?
So just do n plus 1 every single time?
Replace n with n plus 1, n plus 1, n plus 1. This down here are just the n's.
Okay.
Okay? Now, what the absolute value does here, it throws away the negative 1. Okay? Makes these both positive ones. We don't care about that. We can throw that away. We can get this. What we're doing now is testing its positive series. We have n plus 1 squared. I'm going to take this e to the n in the denominator down here and bring it up. Okay. In the denominator here is an n plus 1. E to the n plus 1.
Wait, does the absolute value get rid of the negative?
Yes, it does. It throws them away.
So it doesn't become 1?
These become 1. Each of them become 1.
Because they 1 anyways.
Yeah. And you got an n squared. Okay. You with me? Good deal. Okay. So what do we have here? Limit is n goes to infinity. We have an n plus 1 squared over an n squared. I'm going to group those guys together. Over here we have e to the n over e to the n plus 1. What does that simplify to?
E to the n plus 1.
What is it? I don't know if I heard it yet. What is it?
N.
No.
No,
It's what?
e to the n.
No. 1 over e is correct. Well, you subtract the exponents, but now you subtract n plus 1 minus n. What do you do when you divide numbers with the same base? You subtract their exponents. But to ensure that you don't get negative exponent, you take the bigger exponent minus the smaller. That's the rule you learn, and that's an Algebra 1 thing. Okay? So you take the n plus 1 minus n, and the n's cancel. So you get e to the first down there. It's 1 over e. Okay? Now, we got to evaluate this limit here. We need that limit. They're both going to infinity, but let's see what we can do with that.
You can just subtract any one of them. E to the n minus e to the n plus 1.
Well, you could. You could subtract n minus the n plus 1. You get e to the negative first. But e to the negative first. I'd rather see 1 over e and know that that's 1 over e rather than e to the negative first. You should avoid the negative exponents. It's the bottom line in that. But you're absolutely right, though. Okay, what about this now? I'm going to multiply that out. That's n squared plus 2n plus 1. That's an n squared. A 1 over e. As n goes to infinity, what's this limit equal to over here with the n's? 1. Thank you. Same degree, ratio of leading coefficients, 1. Right? Or use L'Hopital's. When you take derivatives, you'll end up with 1. You get 1. This limit is 1 over e. 1 over e is less than 1. The series converges absolutely. Okay? Converges absolutely. Because what we just proved is that its positive series, the thing without the negative ones, converged by the ratio test. That's what we did.
What rule did we do that where if it's equal to 1 or less than 1, it's diverging?
We did a limit comparison test where we took a known series, compared it to another, and took the limit of one term over the other term. As long as that limit was greater than 0, not infinity, the series converged or diverged together. That's the closest one we got to that, I think.
Which one was like if it's 1 or equal to or less than 1 and diverges?
Oh, okay.
That's what
That is the shortcut for difference in degrees. That was the shortcut that I gave you. Here you go. That's a P series.
It's going to be confusing a little bit.
Well, I'm going to give you another rule, too, which may add to the confusion. But here's what I'm telling you. I'm just saying, yeah. If you had this series, infinite series, here's what I told you to do. Difference in degrees is 1. You take the denominator degree minus the numerator degree always. That difference is 1. Because that difference is not greater than 1, okay, this diverges.
Mm-hmm.
This diverges.
Okay. Yeah.
That's what I think you're thinking of. Now, if you had to prove this, okay, what you would do is compare it with a limit comparison test with the known diverging series 1 over n, the harmonic, with the same difference in degrees. And you would prove that they diverge together. 1 over n diverges, this one diverges. They have the same difference in degrees. And the other thing, just because this is really important, this is a lot of series can be analyzed this way. If you had this one, oh, okay, what about the, I might as well do it.
1.5 minus 2 is negative.
Yeah, and that's not good enough. This diverges. If it's negative, it definitely diverges. It's always bottom, the denominator minus the top. And if you had this one, let's do a couple. Let's make sure, because this is a way to do a lot of these series. Let's suppose we had this one.
That's converging.
This one converges because the difference in degrees is 1.5 greater than 1.
Now, could you use the ratio one for all these?
You could use a ratio test on
I
this.
know it's harder, but
Yeah, you could.
tougher, but
You could use a ratio test. You want me to?
sure. Just
Let's do it. Let's use a ratio test on this one here. Let's do it. Here we go. Take the limit. N goes to infinity. Absolute value. Add 1, n plus 1 to the 3 halves. N plus 1 cubed. Plus 10, n plus 1 squared. Plus 7. That's the n plus first term. Divided by the nth term. N to the 3 halves. Oh boy. N cubed plus 10n squared plus 7. Okay.
Yeah, I'd rather do it something way.
Well, the other way is easier, obviously, but we can do this. It's only another step or two. We can do it. No need for absolute value since we've got positive terms. I have n plus 1 to the 3 halves. This comes up. over, this is down in the denominator, and this is down in the denominator. Now, watch this. It's not that bad. Okay, what about this one here? Let's take the cubes. When I multiply this out, I'm going to have this n cubed. And I'm going to have this, and I'm going to have this. That's 10n squared, by the way. When I multiply this out, I'm going to have an n cubed. I'm going to have various other things in terms of n squares and the like. But the biggest exponent is the n cubed. I get the n cubed over n cubed. What happens to that as n goes to infinity? What's that limit equal to? That is equal to 1. Okay? Now, the other thing left is this guy, n plus 1 to the 3 halves over n to the 3 halves. And what is that equal to? Oh, wow, the test is going to fail here. Wow, it's kind of interesting. This is n plus 1 over n to the 3 halves. Okay, you got same exponent. What happens to n plus 1 over n as n goes to infinity?
1 again, right? Goes
to 1 to the 3 halves. That's equal to 1. That ratio test fails, which surprises me. I didn't think it would fail, but it fails.
Yep.
Which means what? You got to do something else. Which means what? You got to do what we said in the beginning. There you go. Which is kind of funny. All right.
So don't do that.
Yeah. Basically, if you can use the difference in degrees, use it. That's what you want to do. All right, I'm going to give you an amazing shortcut right now that you can use. Listen, 40% of these series can be done with difference in degrees. Another 40% can be done with the shortcut I'm going to give you right now. That leaves about 20% that maybe you'll have to do something with. Okay, maybe. And on the test, it's maybe 1 that you have to do something with. If you can understand these two shortcuts, you've got it. Here. And this is using this fact. It's how fast things increase. That's the key. Natural log functions are very slow increasing functions. Very slow. If you look at the graph of y equals the natural log of x, it comes up like this and levels out. They increase, all right, but it's very slowly. They increase slower than polynomials. Things like n squared, n cubed, and the like, okay? If you have n squared or n cubed, they increase faster than natural log functions do. But polynomials increase slower than exponential functions. As long as the base for the exponential function is greater than 1, the exponential function will increase faster than polynomials do. That's what I said about L'Hopital's a few minutes ago. But factorials increase faster than exponential functions. Okay? And finally, we have one that we haven't even talked about or seen yet, and you probably won't see. Maybe you'll see in the homework. I doubt it, though. The fastest of all of these is the n to the n's. Okay? The n to the n. I'll throw that in there just in case you do run across something like this. The n to the n's increase faster than all of these do. Now, what does this all mean? This means this. If you have this series, let's say you have n to the 5th plus 10 n cubed plus 1 over, let's say, natural log of n plus 1. Okay? Let's take a look at this.
Diverges.
Yeah, exactly. It diverges because you have infinity over infinity, but you know polynomials increase faster than logs do. This is not going to go to 0. This is going to go to infinity. That series will diverge. Okay, here it is. Polynomials increase faster than natural logs. Therefore, the numerator is increasing faster than the denominator. Therefore, these terms are not going to go to 0. And because of that, it's going to diverge. Now, if you had something like this, okay, so this diverges. Suppose you have this. Let's take n to the 5th plus 10n cubed plus 1. Let's say it's over 2 to the n. Now what happens? What's that? It converges, yeah, because the exponential function increases faster. Now, maybe not in the beginning it doesn't. Maybe if you go n to the fifth from, say, 2, where n to the fifth is 32, to 3, where 3 to the fifth is like 729, that increases pretty fast. 2 to the n only doubles. But sooner or later, the exponential function will catch up to and surpass the polynomial. Okay? It will do that, and consequently, these terms will go to 0 fast enough to cause the series to converge. Okay?
Where does the 2 to the n fall in the scale?
It's in here.
Oh,
It's in with the exponential functions. Okay? And if you have something like this, oh, let's take 10 to the n and an n factorial. What will this one do?
0.
That will go to 0 fast enough. This series will converge.
Absolutely.
Yes, it will. It's not alternating, but you can still say that. It's true. All right? Now, yeah, go ahead.
What does E stand for then? I'm not really sure. Like, you have exponential just means that it goes to the end.
Exponential means we have a constant base raised to an exponent.
So when we're doing this, this E, what does it even stand for?
E?
Like
2.71828, 1828, right? 45, 90, 45, 23, etc. It's a base for the common logs. Okay?
You've done these a lot, haven't
Yeah. Yeah.
So it's this base of logs.
Yes, that's what it is. Now, where's the problem? Where's that other 20%? I said 40% difference in degrees. Just look at the difference in degrees. Another 40% relative rates of increase. We'll do it just like that. Okay? The other 20% is when you have combinations of these things. Okay, let's do one.
Is this like the next section?
No, this is still ratio test. Okay, still ratio test.
Yeah, definitely.
What's that?
So you think it's going to be a long night?
Nothing. We're practically done now, for crying out loud. Here's the problem. Let's suppose we have n cubed 10 to the n over an n factorial. This is a problem. The problem is because n cubed over n factorial, no question, that converges. N factorials increase faster than n cubes, polynomials. And the factorial increases faster than the exponential function. But the product of those two up there, a cubed with the exponential function, is that sufficient to overtake the factorials and cause the series to diverge? That's the issue. Would you say? No, he says no. And he's right. It's not. It's not. But that's where the problem is when you get combinations. Certain combinations will work and increase faster. Let's prove this. This is one of those 20% ones that you really have to use the ratio test. Okay? So let's do it. We'll take the limit. B goes to infinity. The thing is, on your test, I probably don't have a one of these at all. Probably every one on the test can be done by either difference in degrees or relative rates of increase, I think. Although you may have one of these. I don't know. All right, let's take, no need for absolute values because, again, these are positive series. I'm going to just use parentheses. We're going to take the n plus first term. Bless you. Over the nth term. We're going to find the limit as n goes to infinity. I knew I would do that. I'm sorry. That's an n going to infinity. It's muscle memory. When I write that limit, I want b to go to infinity because I'm thinking improper integrals. Okay? I knew that was going to happen. Take the limit as n goes to infinity. We have a numerator, n plus 1 cubed. We have a 10 to the n plus 1 up there. We have an n factorial that comes up there. Down below, we have an n plus 1 factorial. Oh, let's see. Let's put it in order. N cubed, a 10 to the n, and an n plus 1 factorial. Okay? And let's evaluate each one of them.
So you got n cubed on the top and bottom.
Yes. So that limit is equal to what?
1.
Yes, it is. So we got a 1 out of these two guys.
And then
10 to the n plus 1 over 10 to the n gives us
10 to the n, right? On 1. Oh, no, not 10 to the n. 10 to 10.
10. Okay. Then I have an n factorial over n plus 1 factorial, which gives me a
Okay, n plus 1.
n plus 1 on the bottom. Very nice. Nicely done. That limit's equal to
If it goes to infinity, so it's 0.
0, which is less than 1, therefore converges. Okay? And that's
Nice.
exactly what he said, okay, what Vitali said, because it's not sufficient, that product, to overtake the factorials.
He's a mastermind.
I know,
Yes.
it's really good.
He is good.
Thinking about
Right.
computers and calculations.
What's that?
What if factorials go again?
Here's what happens with the factorials. You got an n factorial, you've got an n plus 1 factorial. And what you should realize is that n plus 1 factorial is n plus 1 times n factorial.
Oh, I got you.
And these cancel. All right, that's the ratio test. We have one more test for convergence, and that's the root test. Root test?
Today, right?
No. No. Root test. If you're given a series, there's really no restrictions on these terms here. Okay. Then take the limit as n goes to infinity of the nth root of the absolute value of the nth term. I know, it's kind of crazy. It is crazy. The nth root of the absolute value of the nth term. And let that limit equal L. There's a very specific examples where you use the root test. I'm going to tell you that in a minute, but let me tell you what the root test is. Then, what can happen? Then, you got three cases. If L is greater than 1, the series diverges. If L is less than 1, the series converges.
Absolutely.
It would be absolute convergence because you're taking an absolute value. That's true. It's just generally you don't have alternating series in there. If L equals 1, the test fails.
So it's the same thing as the other.
Same exact thing as the other. Now, when do you use this test? There's one specific case when you use this. You use it for series like this.
This is like 1%.
Yeah, it's not very often, that's for sure. It's something like this. Oh boy, that's an obvious example. Well, let's do it anyways. This is the sum of 2 plus n to the nth. You use the root test when you have an exponent of n out here by itself. Why? Because the root test, by taking the nth root of that nth term, it cancels that n.
And then you just do the absolute value.
And then you just look at the other one. So here's what you do.
Can this go?
Nth root of the absolute value of that nth term, which is positive anyways, you don't even need the absolute value. But what happens to the nth root when you raise this to the nth power? They cancel. Yes, they do.
So this one goes to infinity.
Yes, it goes to infinity, which is greater than 1, consequently diverges.
This may go not to infinity anyways.
What's that?
This function can't go anywhere else.
I can't converge.
Yeah, I know, because right in the beginning here, this is not going to go to 0. As n goes to infinity, these terms are going to infinity rather quickly, so they certainly can't converge. They will diverge. But what I'm saying is, if you have something to the nth power, this is the only time you use the root test, okay, is to cancel out that n. You'll see it on the homework. I think there's a couple there.
Can you give another example of this?
Yeah, a better example? Is that what you meant to say? I don't blame you. That's probably, all right, let's see if I can think of another one here that's better. That maybe even cause you to think a little bit here. Well, let's see. They're obvious. They're all so obvious, though. It's oh wait. If I get rid of that,
Just go on the website.
well, see that one.
They always do something unobvious.
Yeah.
Preposterous.
I don't want to do that, but maybe you will. Wait, Gester, you have WebAssign there? This is on the ratio test and root test. You got a 2-tron? Give me one. You can give me one with a, maybe it says use the root test to do something. I'll do one out. If you can find it, this is 9.7, 6, whatever it is. Ratio test and root test are together. If you can find one there where it says use the root test.
Would it be like the same exponent on the bottom and the top or something? Or
Well, could be. Could
One
be.
over
Okay.
the n,
1 over what?
n to the n. I guess that's.
Okay, this is interesting. 1 over n to the n. Wow. This is obvious, too, though. All
Alright.
Do you take the square root?
Well,
right, well, let's do it.
Negative 5n over 2n plus 1
All right, negative 5n,
over 2n
2n,
plus 1
plus 1
to the 3n.
to the 3n power?
Yup,
Wow. That's it right there?
that's it.
Okay, let's do these
So
two.
you take the square root of 3n.
Here's what you do. Let's take this one first. You take the nth root of this nth term, okay? When you take the nth root of this thing,
Oh, you still take it over the top though?
okay? What happens here when you take the nth root of this thing? It becomes 1 over n. And you take the limit as n goes to infinity of this nth root of the nth term. That's equal to this limit of 1 over n. What happens is this and this cancel out, okay? They cancel out here. So you get 1 over n. As n goes to infinity, that's 0. Less than 1, that one will converge.
Well, the square root of 1 is 1. So
Correct.
That's why that works. Right?
Well, this one works because the n to the n, my goodness. These terms are going to 0 so fast it's not funny, all right? This series will definitely converge without using the root test, but there's a root test. I'll do the other one too.
do you take the root of 1 as well? The n of
Yes.
1?
That's just 1.
Okay. So any kind of root of 1 would be 1.
Yeah.
What's the
I don't know how to tell you this, but I just lost my pen. Wait, what happened? Where'd it go? It ate my pen. Wow, I don't know where it went. That's crazy.
Glass over.
Oh, we have too many pens.
I have another pen. But wait, something just fell.
What's the thing to this?
Well-
Section, so
Wow, that is so weird.
you don't understand.
That was a nice pen too. All
So
right.
you lose a lot of
Actually, I'm
pens,
starting
and you
to-
talk about that last
Oh, I lose pens all the time. Okay. Okay, here, let's make sure we're okay with this. This 1 over n to the n, you could rewrite it as the nth root, oh, this pen's not as good, is n to the negative n, right? That's what 1 over,
I think it's a fall underneath.
Move the-
where, all the way down? Yeah, I couldn't, well, yeah, let me try this pen. I got some more pens. I've been accumulating pens. Okay, this is equal to n to the opposite of n. Oh, this is probably better than the other one. To the 1 over n. What do you do with the exponents? Multiply exponents.
Yeah, this one is better.
Okay? And you get 1 over n, like I said. As n goes to infinity, that goes to 0, it converges. Let's do the other one. The other one's kind of interesting. Let's do this other series. Let's try this one. N equals 1 to infinity. Okay. We have negative 5n over 2n plus 1 to the 3n. We'll take the limit as n goes to infinity of the nth root of the absolute value of the nth term. Okay. Now what that does is makes this a positive number here. Okay? So we end up with the limit as n goes to infinity of 5n over 2n plus 1 to the 3n times 1 over n. That's the nth root, is when you raise it to the 1 over n, like I did here. What happens here? These guys cancel. You get a cubed here. Okay? Everybody see that okay? This is 1 over n to the 1 over n power. This is to the nth power. They cancel. You're left with a cube. What's this limit as n goes to infinity of 5n over 2n plus 1 cubed?
125 over 8.
2.5.
What is it? What happens as n goes to infinity?
125 over to 1.
Oh, it diverges.
Yeah, diverges. This goes to infinity. Listen, you got 5 halves here. Okay? Oh, yeah, it goes to, no, all right, I shouldn't have said it that way. You have 5 halves here cubed, which is 125 over 8. That's what Nick was doing.
125.
Yep. Which is greater than 1, which means it diverges. Okay? And you're done.
They all diverge.
Nice.
That one diverges. This one converged. Okay? Because 1 over n is going to go to 0, so that one converged. And this one diverges. Yes, go ahead.
Why can't you put like a 3m on when you do the square root thing?
The nth root thing?
Yeah, why don't you put 3m there? That way you can.
This 3n?
Yeah, well, I mean, you don't take.
I don't know what you want to do, Eric.
He wants to put 3n
Well,
in the.
can you put 3 in there instead of just n? Would
It's not
that
the
work?
3n here?
No, the square
Where you
root.
put the n?
On the root.
Back where you were, yeah, right there.
What do you want to do there?
Could you put 3 in there? 3
No.
root? No? Why not?
Because that's not the test. The test is the nth root, not the 3nth root.
Well, because I thought, 1 and 2 and whatever. 3 and
Well, it makes a difference. It could make a difference.
Yeah, because
All right, could make a difference. Okay. That's the root test. Like I said, it's a special thing. You use it occasionally, not very often. It's not that critical. All right, you ready to go on?
So we're done with the tests. right?
We're done with the test. That's correct. We have one more section to go.
That's it?
Yep, power series. Let's do it.
Next class to review and it's in, right?
No, the next class is the Taylor series, McLaurin series. We have one more class of material.
Oh, one more section for this class.
Yes, one more section of information, and then we have review in a lab. That's next Thursday, and then we have the test on this the following Monday.
Nice.
Okay? And then we have review for the final and a sample. I don't know. What,
Yeah, I like that
am I doing that? Is that what I said?
Yeah, you totally do.
I have written.
Oh,
I've seen
fine.
2 people who both do.
All right, fine.
And if we do really good on the practice final, then.
Oh,
On
then.
the video.
Oh, that's true. You got evidence. That's the problem with that thing. Yeah. All right. Everything I say is
Whoever takes this
recorded.
video.
Yeah. Oh, you're in big trouble, man. Uh-oh. And he already picked him up.
Oh, okay, then I'll drop them off at the office.
Yeah, you can do it. Yeah.
All right, thanks a lot.
Yeah, no sweat. I didn't do anything, but. Okay, let's do power series. All right, here's the deal.
Some of these professors you've never seen in my life.
Oh, I've never seen any.
I've been here like 4 years.
Okay, let me tell you this. I've been here for 30 years, full-time. I've been here since 74, part-time, whatever that is, all right? 41 years, part-time, and there's lots and lots of people I've never...
Do they say hi to you?
I say hi to some of them that I kind of recognize that they're here because I see them at faculty meetings or occasionally I'm on a committee with them or something like that. But when we got at faculty meetings, the auditorium down there is filled. 75% of those people, I swear, I don't know at all. I've never seen. But
What about this guy? Who's this guy?
I don't know. I don't know who it is. I don't know. Here's a power series. A definition of a power series. Power series is an infinite series of this type.
We're not gonna say given?
No, that's a definition.
Bad.
That's a definition. Here's a definition of power series. Power series look like this. They have an X in there, okay? Or they could look like this. This is the kind we're going to look at more often than not. But they could be like this as well. Okay. This is called a power series centered at 0. This is a power series centered at C.
Is it always minus C?
Yes, always. If X is equal to C, then you got a whole bunch of zeros there, and that sum is 0. Okay? If X is 0 here, you got a whole bunch of zeros, and that series converges to 0. Go ahead.
Centered at X equals C.
Yes. That's what that says.
So is X and C always, or it's only at that time that it equals 0 when they're the same?
Yes. Yes, it is. Here's what we're going to have to do. Let me write out some of these terms. Here, we're going to take these primarily, but I am going to mention this. What do these series look like? When n is 0, we get a sub naught x to the 0, which is a sub naught. Then we have, when n is 1, a sub 1 x. And we have a sub 2 x squared, a sub 3 x cubed, etc. That's a typical power series in X. Let me give you a specific example. A specific example would be one like this. Okay. Here's a power series. Centered at 0, it looks like this. Okay, when it's 2, we get x squared over 2 squared, 4, yep. X cubed over 2 cubed. Okay, etc.
Okay, so it just has to have an X over N pretty much. That's all it needs.
You have to have an x to the n, and you have to have some constant. Okay? Now, here's what we're going to be interested in doing. What we're going to be interested in doing is finding out for which values of x the series will converge. Okay? Does it converge for one value of x, which is possible? Does it converge only at x equals 0? Does it converge for an infinite number of values of x? From negative infinity to positive infinity, every real number? Or is it limited to certain numbers? Okay? Does it converge? It's called a radius and interval of convergence. That's what we're interested in. Let's do one. Okay? You ready? Let's take that infinite series. Anybody have an idea of which values of x this series will converge, just by looking at this right now?
1.
It does converge when x is 1, that's true, but that's only one value. There are others.
Also, it can converge at other. Are we looking for like the
Yeah.
0.
X can be anything else.
Well, if x is, does this converge when x is 5, say? And the answer is no, because you get 5 halves to the n, and that's a geometric series whose ratio is greater than 1. I'm going to show you. I'm going to show you.
Automatically start diverging?
What's that?
Doesn't it automatically diverge as soon as you hit an exponent? For this case?
No. It converges for some x's, it will diverge for others.
Anything less than 2 or equal to 2?
Well, that's not too bad. What about for x equals negative 3?
No. Greater than -2.
Okay, between negative 2 and 2. He's exactly right.
That was his answer.
Oh, that was yours? Wow. That's exactly what we're going to find out. How do we do this? How do we analyze these power series to find out for which values of x it converges? We use a ratio test. Okay, so let's take a look at this. We're going to use a ratio test on this. We're going to take the limit as n goes to infinity of the n plus first term over the nth term. And what we want to do is find the x's that cause this limit to be less than 1. Because it's those x's that will cause this series to converge by the ratio test. This is the ratio test. And for the x's that make this less than 1, this series will converge. Okay? So let's see what happens. X to the n plus 1. 2 to the n comes up there. X to the n down here. 2 to the n plus 1. Okay. With me? Alrighty.
No, don't.
Okay.
No.
X over 2.
Sorry, I'm not done yet. I'll try. No more.
That's right. You're right. All right, ready?
Nope.
No. Okay.
No, I don't get why you guys are laughing. 'Cause you gotta.
Why I get what? No, because I said yeah, and I was going over Ludmila's head
Like, I don't get it.
to Vitali. I was going like this over there. All right. Okay. Here we go. Let's simplify this.
Wait, did the other one have absolute signs on the... Can you just show that again for a second? Oh, yeah? Okay.
Yep.
Keep going. Sorry.
Okay. No problem.
This is x1.
So we end up with x to the first, or x, over 2. Now, we're taking the limit as n goes to infinity. There's no n's here. Okay? What's that limit equal to? That limit is the absolute value of x over 2. Since there's no n's. The absolute value of a quotient is the quotient of the absolute values. I can rewrite it this way. And I can take this 2 on the other side. Whoa! Whoa, whoa, whoa. Easy. 2. Sorry.
It's a long day, Vern.
It has been. It has been a long day. It's true. Okay? That tells me this. As long as x has an absolute value less than 2, that series will converge. Okay? Now, what we're going to do is rewrite this way, without the absolute value symbols. If the absolute value is less than 2, then x must be between -2 and 2. What this 2 gives me is called the radius of convergence. It's a radius of convergence. This is an interval of convergence. Okay. There's one thing, however, the endpoints. What happens at the endpoints? When x is 2 or -2, when I put a 2 or -2 in here for x, the absolute value of 2 over 2 or -2 over 2 is equal to 1. And what happens to the ratio test if that limit is equal to 1?
Fail.
It fails. That means what you have to do is test those endpoints manually. In other words, take x equals -2 and go back to the original. The original was this. And put -2 in for x. And see if it converges or diverges, because the ratio test fails. Now what happens here? This is equal to this. Yeah, you end up with this here. And what about this series? -1 to the n as n goes from 0 to infinity. Does that series converge or diverge?
Wait, when n equals what?
This one right here.
When n equals what?
How did you end
N goes to infinity. I want to know this series. This series is what? 1 plus -1 plus...
Diverge?
Yes, it does.
Because is it, if n equals 0,
That's correct. What the problem is, the limit as n goes to infinity is not 0. Okay, it goes 1, -1, 1, -1, 1, -1. There is no limit as n goes to infinity. If that limit of the nth term is not 0, forget it. The series will diverge. This series diverges. So that endpoint is not included in our interval of convergence. It diverges at that endpoint. What about the other endpoint? Does it converge or diverge at that endpoint?
Do you only check that endpoint?
You got to check the 2 endpoints for interval of convergence. Now, fortunately for you guys, on your test, I'm going to ask for radius of convergence. You don't have to test the endpoints. But on WebAssign, on your homework, I think it will probably ask you for interval of convergence, in which case you have to test the endpoints.
Not on the final? Are we gonna?
No, on the final, no way.
No way.
No way, because I give you pretty easy problems on the final. Okay, 2 to the n over 2 to the n, that's equal to the sum of 1s. And if you got an infinite number of 1s, I'll tell you what, you do not have a converging series, you have a diverging series.
So what does this mean?
This means that this is the interval of convergence. Don't include the endpoints. Some series will include the endpoints. Some will not. This one does not.
Is there ever this less than or equal to?
Yes. Yes. It's possible to be a less than or equal to on a series. It's possible.
So we're gonna do problem of one.
Can't think of one, but there is possible. What's that?
We're
Can
gonna
you
do
give us an
problem
example?
where we have to find the radius and the interval.
Yeah, let's do now this is one of them. There's 3 cases that's going to happen. This is one case. This is a radius of convergence that's equal to some real number. It's equal to 2. That means from -2 to 2, those numbers in there, not including the endpoints, the series will converge. Okay? That's an r equals 2. Let's do another series. There's 3 possible cases. Okay, let's do another one right now. Here's another one. We're almost done, actually. Okay. Almost done.
I'm listening, I'm just tired.
I know, I can see some people fading away here.
Could you see me falling asleep? I was trying.
What's that?
Could you see me falling asleep?
Yeah.
I was trying to sit waiting.
I know you were.
It's hard, but when you're in the front row, it's.
I know. It's true. I know. You're very honest, you know that? You're an honest person. I
In
didn't
high
see
school,
that.
What am I gonna lie?
whatever
What am I
you
gonna
try
say?
doing,
I know.
As long as the teacher doesn't see your eyes.
Yeah, there you go. Yeah.
in front of you as if you're reading.
Yeah. All right, let's try another one. Let's do another power series. Oh, let us do n factorial x to the n's. Let's try this one. We want to know for which values of x this power series will converge. We're going to do it with, now, any ideas first before we do it?
The ratio,
All of them.
ratio.
What?
All of them,
All reals?
except for 0.
Except for 0. So wait, what are you saying? It converges or diverges for all reals except for 0?
Diverges for everything except.
Okay. You nailed it. That's exactly correct. That radius of convergence is 0. It converges only when x is 0. Otherwise, it will die. How did he do? I don't know. How'd you do it?
Yes, it did.
He's good. He's good. He's good. He's good. Let's do
Yes,
it.
an old Burns test.
Oh, there you go. All right, let's take a look at this. Here's what we're going to do. We're going to take the limit as n goes to infinity. Okay. Absolute value, n plus first term. X to the n plus 1. Okay. Over n factorial, x to the n. And we want to find the x's that cause that limit to be less than 1. Okay. So, limit, n goes to infinity. Let's see what happens here. We have n plus 1 factorial over n factorial. What does that give us?
Wait, don't you flip them over or we don't?
It's the n plus first term over. There's no fraction here, so there's nothing to flip
N
over.
plus one
Yes.
on
I have
top.
a question.
Go ahead.
When
Yes.
this is gonna be on the test, are there gonna be numbers or things?
No, it's going to be just like this. Just like this. Yep. For the power series, you're going to have an x.
So it's n plus 1 and x.
It's n plus 1 and an x. Very nice. Now, n's going to go to infinity. For which values of x will this limit be less than 1? And I'll tell you, for which values of x will that limit be 1? N's going to go to infinity. I don't care what you take for x. As long as it's not 0, that limit will never be less than 1 for any value of x except 0.
What about negative one?
It doesn't matter. If you let x equal negative 1, you're going to have n going to infinity. You had a negative 1 here. That's going to go to negative infinity, not less than 1. Okay? It doesn't exist. Negative infinity simply doesn't exist. Okay?
No,
All right.
what I'm saying is.
I mean, it's not a real number, so the limit doesn't exist.
When you go to infinity, technically you're taking all the terms, right?
You keep on going.
But wouldn't it at negative 1 it would equal 0?
At negative 1 here, when n's going to infinity, well, first of all, you're taking an absolute value.
Oh.
So x is going to be 1 anyways.
Oh, okay.
Okay? So let's use that argument. This, forget that. Okay, this will converge only at x equals 0. Okay? That's the only x that causes that to converge. Every other x will have a limit that's not less than 1. Okay? This radius of convergence is equal to 0. The interval of convergence, which is what WebAssign may ask you, consists of the single point x equals 0. Okay? The single point. So there's a case where you have a radius of convergence of 0. Let's try one more. And then we're done.
Wait, what is it? Single point of 0?
Yes. This converges only at x equals 0.
So in WebAssign it'd be 0, just right, 0.
Yeah, well, however they ask you, yeah. One more to do. You ready? Let's do this one. Let's do x to the n. Let's put it over n factorial. Let's take a look at this one. All right, we're going to test. Well, any ideas? Well,
Can't you use like that rule again?
yeah, you can use the rule. That's a good point, Nick. What Nick is saying is, let's take a look at this. Here's an exponential function. Here's factorials. Yeah, this is going to converge for everything. Let's do it.
Whenever you do the limit, you add 1. Is that one?
The ratio test, you add 1 to the exponent. Add 1 to the n here. And divide by x to the n over n factorial. We want to find those x's that cause that to be less than 1. So, limit, n goes to infinity, x to the n plus 1, n factorial, that comes upstairs, x to the n, n plus 1 factorial. Okay. All right, what happens when you simplify here?
N plus 1 to the bottom, x on the top.
Now, as n goes to infinity, okay, what happens here? For every real number x, it doesn't matter what x is, as long as n's going to go to infinity, what's this limit equal to?
0.
0. That's less than 1 for every x.
So why is it going to go to 0?
Because the n increasing without bound in the denominator causes the denominator to increase without bound. So for any given value of x, as long as n is going to go to infinity, this ratio will go to 0.
X be kind of almost going to.
No, x is static. But this is really contradictory. X in this expression is the thing that's static. For a given value of x, for some x real number, it's the n that's increasing here, not the x. The x is static, the n is increasing. So for any given value of x, as long as the n is increasing without bound, that's going to be equal to 0, less than 1. This radius of convergence is infinity. This converges for every value of x,
So what do you say converges?
for all real numbers. R, the radius of convergence is infinite. Yes?
Is there ever a case if you don't have anything, like division, say the first example that you showed us, n factorial xn,
Yeah?
would it always be then that it only converges at 0 and nothing else? No?
If you don't have a well, I could write it this way. It's kind of cheating because that's really x to the n over 10.
If you were to write it out right, correct, like,
Instead of being a bozo? Yeah.
Yeah, that.
No, wait, no. Because look at this. Wait, I think I have an example here. Suppose you had this one. Okay, what about this one? Anybody guess what the interval or radius of convergence is here?
You should know. Right. He knows.
It would always go to infinity.
42.
Oh, yeah.
It would always go to infinity, no?
No.
Zero.
There are x's. It converges at x equals 0, but there's other x's for which it converges.
Well, 1 probably.
1, it converges. No, 1, it doesn't converge because you got 1 to the n times n. N by itself will not converge because you're summing up n, bless you,
Yeah, but it goes-
0 plus 1 plus
It
2.
goes up very slowly.
Oh, 1/2. Anything else?
Yeah, 1/2 works. What else works?
0.25.
0.25 works.
So anything under 1.
Under 1?
Under 1, greater than negative 1. Watch
How do you
this.
know that just by looking at it?
Because because this is going to increase without bound, I need my x to be a fraction between negative 1 and 1. So when I raise it to an x1, it's going to decrease to 0 for me. And that way, the only way that's going to happen is between negative 1 and 1. So watch this. Let's go. Here we go. This is the last thing we'll do today. Here we go. And raise to infinity. N plus first term. Nth term. Let x's cause x to be less than 1. Okay. What do we get here? We have an n plus 1, we have an x, and we have an n. Well, n plus 1 over n, what's that limit as n goes to infinity?
Isn't that just 1?
That is just 1. So we get this.
Just get x.
That gives me a radius of convergence of 1. It gives me the interval of convergence from 1 to negative 1. Now, what about the endpoints? Let's check these endpoints out. At negative 1 for x, we have this one.
How does that equal to-
So it just bounces from positive to negative.
Yes, that's true.
So it diverges.
This diverges. Go ahead, Danielle.
Why is the n plus 1 and n cancel out?
Because when you take the limit as n goes to infinity, they have the same degree and their coefficients in front are the same, 1.
Parentheses. It's in a parentheses.
It doesn't matter. This right here, that limit is equal to 1. Use L'Hopital's on it. They're both going to infinity. The derivative here is 1. The derivative is here is 1. You get 1 over 1, which is 1.
Because I thought, if there's like addition on the tab, you can't really like subtract x.
Correct, you can't. You're absolutely right. No, you're right. The rule for exponents and division you can't use. But as far as taking the limits, as long as these are same degree, it's the ratio of their leading coefficients is the limit as n goes to infinity, and that's equal to 1. And like I said, use L'Hopital's on it. The derivative here is 1. The derivative here is 1. You get 1 over 1, which is 1.
Why do you need a computer when you just care?
Okay, what about x equals 1?
Did you move it over a little bit?
You're welcome. If x is 1, you get n, 1 to the 1, you get n here, and that diverges as well. This is the interval of convergence. The radius of convergence is 1. So that one, that would work. Okay, here we go. So, geez, I lost the top of this one too. Oh wait, no, that top goes here. Okay, I lost the other pen. This thing ate my pen.
No, I'm going to find it right
There's no way. It's gone. It's eaten. It's devoured.
now. Need you to sign that, but I'm going to find
So
it.
here we go. Your homework is 9, 6, and 9, 8. Is that about right?
Yeah, you said.
We skipped one. We skipped the Taylor series, and we're gonna finish up on Monday. We'll be done on Monday. So do 6 and do 8.
I gotta.
See you.
You gotta
Yeah, it's
give
gonna-
the numbers.
What-
Like,
What's the first thing
Yeah.
What
on
if it was 2 over 5?
Windows 7?
It would be
First
8 over
Windows
1.
yeah, so it
Yeah,
coverage.
yeah.
Okay. We're done. Kestner.
Hey,
Thanks,
you
Danielle.
can't open this, this is stupid.
No, I don't
There's a ledge.
Oh, is that what it
You
was?
can't open it, so I had to get my hand, it's dusty too.
Oh, here, here's my shirt.
Yeah, this was like.
Unless there's
Thanks.
So over here, this thing's probably. What about you?
That's remember, if the ends are the same decimal degree, then you just take the numbers.
Whoa, how many things are in? Oh, we haven't done that yet. We're gonna do that when we do the Taylor thing.
Wow! Like that thing?
Yeah.
So I can stop on it?
Yeah.
Oh!
Get me ready.